now we're going to build another function that apparently inject inject a f of t into any open sum f of ts, so long as t is an element somewhere in ts. However, nothing about this definition suggests ts must be monomorphic. It can remain the type variable as long as we propagate the member member of t of ts constraint upwards. Okay, so FTS. Oh, cool. Hey, Freeman. I'm not sure if Freeman's around, but three chatters are here. So, hello, three chatters. What's going on? We're working on thinking with types. If you've never been on this channel before, for Sundays, we're in chapter 11. We're about halfway through the book, actually. So it's pretty cool. But thanks for the host. Okay, so the thing about this, though, is that it doesn't look like we're injecting anything, which is a little confusing for me. So give me a second. We haven't done this book in a while, so... Okay, so this is... I see what's going on here. So this is basically a point-free definition, right? So there's really an FT here, right? And you'll see that we're getting an eta reduction because we don't actually need these. So we haven't done this book in a while. So it's going to take an integer, and that integer is the find elem. What does this return if it doesn't find anything? Well, it has to find something because it has to be a member. That's the key here. The result of find elem is a natural number. Well, we'll play with it here in a second. But anyway, this is that piece. So what? Demote, duplicate, delete, lift to top level. I don't understand how to get it to trigger the agelint piece, but that's fine. Okay, so that's inject. It makes sense to me now. Now we have a project function. Yes, member TTS open sum FTS maybe what's F again? K to type. Okay. So project unsafe open sum IFT Okay. I hope type rat shows up at some point. That would be really useful. I hope anyone shows up. Be quiet. Okay. So this is just an integer. This is an f of t. Some type. Open sum string int bool. It's capable of storing string to int and string to bool. Okay. So this is just some type. Where's this unsafe coerce come from again? I assume that's coming from there. Okay, let's try and use this, because I'm a little confused. But I think we're gonna do something like, let's see, set x. Well, we probably don't even need to try set x yet. So first we need to inject to build an unsafe open sum. But what is f of t again? Inject. F of t. Parser. What? Um, What is this supposed to be? Is my chat dead? There's that notification. Let me refresh this page. It's pretty quiet tonight. That's fine, I guess. What is this f of t supposed to be? Hang on. Looking at 3, let me, hang on. This. Looking at 3, we see that OpenSum is a container of f of t, where t has kind k. Because t isn't mentioned in the return type of our constructor, t is existential. Once t enters an OpenSum, it can never be recovered. Knowledge of what t is lost to forever. So f... We're gonna use this later? I'm very confused. We don't use this at all. It's kind of annoying because I'm not really 100% sure how to use it right now. We need an f of t. What if I just do... Can I evaluate that? So that t goes away. Knowledge of t is lost forever. I don't know why I would want this. Okay. Shouldn't I get a maybe? No. But T1 is existential. I don't know what T1 is. Is that right? I think that's right. Sorry, it's a little strange. I need someone to help me warm up a little bit. I think. Hopefully somebody will show up. Or maybe my chat's dead forever. I mean, I can just open this up. Their window as well. Do 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 do. Oh, nobody's around today. It is what it is. So decompose. Hello, viewer. How are you today? If you are feeling particularly helpful, could you just type a letter in chat so I know that my chat is alive, not dead? Not 100% sure what I'm doing right now, so I'm hopeful that it will make more sense here in a little bit. So, N. So I'm guessing this is going to be right. Find elem at T or something. Oh no, we're stripping stuff off. I see. So unsafe open sum n minus 1 t. Interesting. Decompose function lets us perform weak induction over an open sum. Either we will get out the type corresponding to the head of TS, or we will get back an open sum with fewer possibilities. A type tag of 0 corresponds to the head of the type list, so it is unnecessary to call findLM. We maintain this invariant by decrementing the type tag in the right case. In practice, it is also useful to be able to widen the possibilities of an open sum. A new function, weaken, tacks a x in front of the list of possibilities. Sorry, one. Okay. So we're going to try and write this function. Unsafe open some. What do I need this constructor? No. Weaken. What's the idea here? I feel like I'm so lost. So what are we doing? But isn't this is the part I don't understand is I have no idea if this is doing what I want it to do. Do I have to inject? I don't have an F of T. I mean, I can't make one. And this isn't at the be. This N is supposed to keep track of where it is, right? Or does it? It doesn't care because I need to go search from it. Okay. I mean, we can look at the solution. We're just gonna go look. We're on 11.2. Yeah, that's right. one thing that's weird is in his solution, he writes this. Not that it matters, but probably just to match. But fine. I said match, but that's actually the next function we're supposed to be writing. My goodness. I have no idea how we're going to end up using this kind of stuff. Okay, so if we want to perform the same logic regardless of what's inside an open sum, reject and decompose both feel inelegant. I don't really feel any feelings towards them, to be honest. We introduce match eliminator, which consumes an open sum in big O of 1 time. By using a rank n type at 1, match is given a function that can provide a b regardless of what's inside the sum. In this case, inspecting the type tag isn't necessary. There's a general principle to take away here. It's too hard to do at the type level. It's okay to cheat and prove things at the term level. In these cases, unsafe coerce can be your best friend, as long as you're careful to hide the unsafe constructors. I really wish there was some examples of these functions in this chapter. These don't mean a lot to me. I'm having a hard time connecting this to the real world. And I mean, the real world is supposed to be like, we can make these extensible record types. All right. Sure. We probably need all of these things. Oops. And more as well. So we'll just get all this stuff in here. What is this complaining about? Okay, so we need constraint and type. From proxy, we need everything. We need import data vector qualified as V. GHC overloaded labels is label. I don't know what that's for. We never used that before. Okay. And then we need to go in here. Get vector and build. What's going on, Oren? How are you? Oh, I can't spell. I'm a little confused right now. Are you familiar with this stuff? I don't remember if you're one of the superhumans that do a lot of type level programming or not. I finished this open sum stuff and like it hurts my head, I think. Cause I'm having a hard time like connecting this stuff to the outside world. You know what I mean? Yeah. I'm losing this book quickly, and I'm a little concerned. We're not gonna get anywhere. I did write this by myself, but sort of I feel like on accident. And then this one is a wild function. So I don't know. I think this is just gonna be like a practice makes perfect thing. But I'm glad you're here. I'm not. Yeah, glad you're here. We'll just keep trying. I don't know what else to do. So, open products are significantly more involved in their dual sums. Their implementation is made sticky due to the sheer number of moving pieces. Not only do open products have several internal types it's necessary to keep track of, they also require a human-friendly interface. Hang on, I gotta shut that door. Yeah. I think my girlfriend watches her show very, very loud because she's trying to drown out my talking or rambling. So, but then it gets to the point where I can't hear anything. Like all I hear is the TV. I can't focus on what I'm doing. All right, so first we're gonna define a GADT. So this is a okay, so this is actually a data constructor, and this is a type constructor, I think. At least does it works for her. I don't understand that question. I'm sorry. Oh, does it work that she's drowning me out? I think so. Or maybe she's just trying to get me to shut the door. At least I think that's what you mean. Okay, so the implementation we're gonna write will optimize for big O of 1 reads And big O of N writes, although other trade-offs are possible, we thus define open product as a data vector of any's. Yeah, I got it. So we're going to make an open product of any's. Type All right, so F is the type of what we're storing. And TS is a list of symbols and their values. So I think this is the dictionary. Hopefully this will make more sense towards the end. So the parameter TS now pulls double duty. Not only does it keep track of which types are stored in our vector any, but it also associates names to those pieces of data. Yeah, I think this is where we're going with the dictionary style. We will use these symbols to allow the user to provide her own names for the contents of the product. He wrote his, so obviously I should say her. Creating an empty open product is now possible as an empty vector and an empty list of types. So nil okay. And so this thing here should have type any of F. Yeah? Yeah. Okay. And can we get diagnostics on this F? Just as local. Okay. Interesting. Because all data inside an open product will be labeled by a symbol, we need a way for users to talk about symbols at the term level. Key, symbol, key. Okay. By way of type applications, key allows users to provide labels for data. For example, key, so key allows users to All right, interesting. So that's how we're gonna label. This is later on page 151, which is coming up in 4 pages. We will look at how to lessen the syntax to build keys. These are the necessary tools to insert data into an open product. Given a key of key and an f of k, we can insert a key k into our open product. So hopefully this will make more sense. I feel like the open sum was a little detached from reality for me, but I think I'm following now. And there's also some examples, so that should help quite a bit. So that's the thing we want to put in there, the f, right? K, T. Okay, so let's write this undefined and think about it a little bit. All right, so this T is the thing we're trying to put in here with a key. That key. So, for example, this. And remember, just if you forgot, symbol is just a type level string. And then obviously we need an open product to insert into, and then we can create a new open product. All right, I think I'm okay with this. So, wait, why do we ignore the key? Seems weird. Open product. V for vector, sure. We build a new open product. We cons an any ft with v. Interesting. Okay. So this type level shenanigans you don't even see, really. I mean, it's kind of abstracted away from you. You don't even care what this key actually is, because really all you need is the fact that it's a symbol so that you can get it. Right? So this key here is a type level string, so you just use it. And then we're giving an f of t. And if we give it an f of t, it gets us any of f, which is what's in our vector. And we're prepending it to ts. Okay, I think I'm following again. Is everyone okay? If you have any questions, speak now or forever hold your peace, because this stuff's not easy. The open sum was much more confusing to me. I think that maybe the terms of the functions were the part that was confusing. I'm not sure. Or maybe I just didn't understand. All right, let me read this, but I think I just said it. Our function insert adds our new type level tuple, key of k, key and k. I was talking with someone on Twitter about terminology, so I'm trying to think more carefully about it. To the head of the type lists, and inserts the fk to the head of the internal vector. In this way, it preserves the invariant that our list of types has the same ordering as the data in the vector. We can test this in GHCI with the t command. Oh, wait. silly me. Oh, app through G some oh my goodness, I can't type today. Stack build stack couple. Wonderful. Okay. Hey new viewer. If you've been here before, we're just working on thinking with types. If you haven't been here before, we're doing type level programming in Haskell. So this is going to be probably a little wild if you've never seen anything like this before. But I'm doing my best to explain it, mainly because I need to explain it to myself. So feel free to ask questions or just say hi, whatever you want to do. So we need a type level key. So we'll just like put a random key in here. And then we need a value, which I think is just hello in this case. And we're going to insert this into an empty dictionary, essentially. I think I need... That's a parse error, which is a little weird. Maybe I need to turn on type. Oh, I also don't need a lat here. So let's do set x, I think it's type applications. Yep, and then we need type applications gets us access to that ampersand syntax, and then I think we need data kinds, apparently. So then if we look at the type of result, we'll see we have an open product of maybe. Why do we need this maybe here? That's one thing I don't understand yet. Maybe it will become more obvious. And then we have a list of our types. So we have our key, which is just key in this case, and then a string of values, right? So that, well, it's storing this, but obviously the type of that is string. Okay, interesting. And then we can insert another thing, but I think, oops. I assume I have to write, well, we'll use a different type here, but I think we still need maybe. And then the result. Yep, so here's the other key value pair. And then they point out that there's one issue with this, is that you could write something like this, and then you get two things with the same key, which is obviously problematic. So, you can't do that. So it says, trying to insert a duplicate key into an open product succeeds. Well, this isn't necessarily a bug. It's confusing behavior for the user because only one piece of keyed data will be available to them. We can fix this with a type family, which computes whether a key would be unique. So let's do that. So type unique key k ts t null. That behaves like, sorry, I'm not sure yet. We can try something else. I think we just need a data constructor that takes something. So I think you could literally put anything in there. Let's try it here in a second. Yeah, I think you can, because I tried it with the open sum and I was able to do it. So give me a second to finish this. Tie equal key flip Clydesy first TS. Okay. So this is a composition operator. This behaves like dot, and this behaves like $sign. So I think null is just is null, or something like is null. Let's whip out some Hoogle here. I think it's probably from here. Yeah, this has to be it. Okay. Yep. So it's just checking for an empty list. So that's all it's doing. Okay. So this is just checking for an empty list. And then we have a TS, which again is this right here, a list of these things. So we're going to filter, right? So we're going to go in and filter first, which is K, and then we need to check if it's equal to our key, right? So this is a composition. This is a type level filter, similar to something like this. Filter equal key dot first list of keys and values. Well, it doesn't even matter. Just, you know, tuples. Right? That's what that is. And then again, null is the same null. So it's like an is null type function. And this returns a constraint, I believe. Hang on, I will tell you. Yes, it returns a constraint. So now we take insert, we modify insert. So let's actually just comment this out, which is GC. And we will rewrite this insert. I should just copy it here and put it here. So with no, you can put a $sign there. It's basically that. With unique key, or let's write it this way. We can use unique key to ensure keys are not duplicated. Oops, there's no way I typed that right. There we go. And so now we have unique key. Oh, and we need eval. Wild. Okay, and now we need to go back to Oren's question. Also, hello, third viewer. How are you today? Feel free to ask questions if you're a little confused, because I'm a little confused as well. Maybe you're not confused. It might be a machine. Okay, and then we're gonna go to the REPL and we're gonna try Oren's thing first. So let's do that. Oh, we need some set type applications. We need some set. Oh, I can probably do that in one line, can't I? Data kinds. And then we need to do this. Yep. So type result. And you'll see that list right there. I'm not sure exactly what it does yet, Oren. So it might just be one of these things that you need to make all the machinery work. I'm not 100% sure though. We've been using just quite a bit, so there might be something that I'm missing here that I just don't remember. Anyway, we should be able to. We shouldn't be able to insert something with the same key now. So key at key. Just no. True. Result. And then what if we just stick a random F in here? Does it give me a different error? Yes, it does. Yep. So there's the mismatch. So it does matter, but what it's used for is not 100% clear to me at the moment. So we'll just keep moving on. LS, I'm a goofball. Okay. This it fixes the bug. Informative it is not, but at least it fixes the bug. In the next chapter, we'll look at how to make this error message much friendlier. So that's cool. To project data out from an open product, we'll first need to write a getter. This requires doing a lookup in our list of types to figure out which index of the vector to return. The implementation is very similar to that for OpenSum, except that we compare on the key names instead of the Ks themselves. So we're going to write a type find lm key symbol ts list symbol t k equals eval from maybe stuck. So that protects us if it can't find anything. Find index type equals key composed with first again ts. Missing parenthesis. This is not this. We need the type level from maybe, not the term level from maybe. Okay, and then we can write our function. ETS known nat find lm key ts int I don't know that we put this on the left before. Maybe we have. Integral dot atval proxy Does findLM return an integer? I assumed it was going to return whatever the type of the T was, but okay. We're probably going to write that next. So this gets us the location of where the element is. Okay, so we will also require another type family to index into TS and determine what type to return from get. Lookup type returns the K associated with the keyed symbol. So we're gonna do that. So we need type lookup type key K TS KT from maybe stuck lookup key TS. Okay, so lookup must just exist in the first class families package. It's got to be coming from there. And this is just getting us a type. Okay. Yes, F. Okay, so basically make sure that this key exists in the open product. You probably can't read this anymore. Hang on. Yeah, should do it this way. Okay, you should be able to read it now. Lookup type key TS. So that gets us the type we're looking for. Oh, we're done. So get, this is the return type, right? So we're gonna get an F. Oh, okay, I see. So that's where the F is. So this is gonna return a just of whatever, I guess, or a list of whatever. So that's why it's there. Unany v dot unsafe index v find lm at key at ts. Unany any a equals unsafe coerce a. This is pretty wild. So where does this unsafe index function comes from? Why do I need to unsafe index? Maybe it will say, hang on. So he at So I think this returns a just. Let's try it, because I really want to see what this returns. But I think it's going to return us a just, or well, a list if we use list. So we want our result. Well, we need this and that. We need this, but let's not use a list. Let's use just, because I want to see. And then we're going to get the key from result. Weird. There it is. Okay, and then if we put hello in a list, can we put two things in the list? Probably. There you go. So that's what that F is for. Does that kind of make sense? I mean, I don't know that it makes sense, but we're seeing it in action. How strange. Okay. Excuse me. Okay, so as one last example for open products, let's add the ability to modify the value at a key. There's no constraint that the new value has to be the same as the old one. As usual, we begin with a first-class family that will compute our new associated type list. Update elem scans through TS and sets the type associated with the key to T. So type update elem key symbol. A lot of folks just hopped on, so hey everybody. My name is Barry. On Sundays I do type level programming in Haskell. We're gonna be here for another 50 minutes or so. So feel free to hang out, follow, whatever you want to do. Feel free to ask questions, because this is kind of a strange topic. Yeah. So T. Oh my goodness. Type K. TS is, yep, the same as before. Symbol K. Set index. Okay. So we are going to update the symbol here. With a value. These aren't the same K, right? I don't think so. So this is the new value, or well, the new type that we're basically replacing. So wherever we find that element, set it to this. in TS. Weird. Okay. So let's see if we can write this. So it's going to be, oops. Key TSF no nat find elem key TS. So that bit says basically make sure that the key that you're asking for exists in the list. That's what it's doing. Otherwise, you know, you should just fail. Then we need a key. Yeah, put that there. We need a key. We need a value. We need an open product to insert into. And we need an open product to return. So this is going to be where we use update lem key t. But we also need t here. Makes sense, right? Because these two t's need to be the same t's. Key t ts. Oh. I need to evaluate it. Otherwise, it doesn't work. All right. Yeah, so here, when we're doing these, I forget what these are just first class families, yes? No, type family. When we're doing these type families, you don't need eval, but when you actually need to compute the type, you need to eval. Okay, so in this, I have a feeling that we don't care about the key again. I'm trying to write this myself. I think I can. And we need an f of t, and we need an open product of v, probably. Yep. We're gonna build a new open product. And this part I'm not super familiar with. v dot slash slash interesting. So I think this is a disjoint. I don't know what this does. Let's go look. That's not going to help me at all. Text message, hang on. Okay. So we need to find for each pair IA from the list. Replace the vector element at position I by A. So oh. What? Why is this not replaced? Oh, because there's a 2, 8. I get it. Sorry, that threw me off. So 2 would get replaced with 1, 0 gets replaced with 3, and then 2 gets replaced with 8. Okay, I've not seen this function before, so that's new to me. But anyway, it makes sense. It's a bulk update function. Wild. Okay. Next thing we're gonna do is implement delete, which probably means we need to write a type delete elem, which is gonna look a lot like this one. There's probably a delete index or something. We probably don't even need. Seems to type check, but we should probably go double check that this is actually a thing and what it's doing. That's not what I want to do again. I wasn't using Google that time. So type level version of delete index. But this does not say it's in first class families. So how does this actually type check? No, it doesn't. So we need to go find set index, probably. Because I need to go figure out how to delete stuff. So it's gonna be this one, and it's gonna be do we just, are we supposed to just delete the value? I'm confused. Do we need to write a set index function that deletes? Or do we just leave the key there? Not really sure. Hey Freeman, how's it going? Thank you. I'm happy to be streaming as well. Thanks for the host earlier. I'm a little lost of what I'm trying to do here, so we're sort of collecting our thoughts. We need to write some sort of delete lm family. Oh, nice. Yeah, I think I added you to mine as well, if I remember correctly. I probably did it wrong, but I think I tried to add you anyway. We need to compute the new type by removing it. There's got to be a function that removes an item from a list, right? Have we used it yet? We may have used it already. So we could filter. Where's that filter function? We used that before, didn't we? Oh, I'm sorry, I just hit my mic. Hopefully that wasn't too loud. So we could use filter to filter it out. We could use exactly this, I think. Yeah, I think that's right. So what this is doing is just saying, look, give me back the list of types and filter out the one I'm trying to remove. Then all I have to do is delete it from the list via something like this. And so this is probably going to look just like this, more or less. So let's grab that. Delete. And then instead of update lm, we're going to use delete lm. And everything else stays the same. We just need to create a new open product where we delete the actual value. So we got to go look at vector. It's not vector. Google data vector. There. And we need to look at some sort of deleting function or safe destructive updates. I mean, I can filter it out as well, but there's got to be a better way to do that, right? Delete. Does anyone know the function for removing something from a vector? I can filter. That's totally fine. I'm just trying to save myself time. Filtering, partitioning, searching, folding, conversions. Let's just use filter, I guess. Can I filter? Probably. So v.filter v. I need something here. Now that gets us the index. That's not what I want. There's got to be a way to remove. I don't want to filter something. I want to remove an index in a vector. Haskell. Gotta put vector in. Another new post. Fine with new posts. And we can just write this. Delete at, or whatever. This is, vector is mentioned one time in there. Wonderful. Data vector mutable. Nope. Not what we're looking for. So this would get us the value. We could filter it out from there, but it seems like there's got to be a better way to do it. Let's just write that and see if it works and go from there. I'm just trying to write something and see if we can get it to work. So just give me 1 second here. Oh. There has to be a better way to do this. Why is there no v.drop function or something? That would save me a lot of time. There is. I'm an idiot. It's literally in front of my face. Oh my gosh. v.drop. I looked for delete and what else I look for? I think remove, but I didn't look for drop. That would have saved me a lot of time. So anyway, this is going to be find lm at key at ts and b. Cool. So that is the type level version of delete for an open product. And if you're not following thus far, I noticed there's a few people watching again. So hello. We are trying to basically implement Python dictionaries in Haskell. That's what we're doing. And this, by the way, comes from a book, Thinking with Types. If you've never seen it before, you can get the book here. I'm going to be here for about another half hour, so feel free to hang out. Book. There's the book we're working on, and the code, if you want to keep reading, is there. And also, I put all the previous chapters on YouTube, but I forget what the... Oops. I think... Oh, it's just YouTube. So, there you go. So, anything that you want... if you want to go learn about type level programming in Haskell, you can start from, I think there's now like 10 videos on the YouTube channel for these things. So if you want to go from the beginning, you're welcome to go from the beginning. You're welcome to hang out and ask questions. I'll try to do my best to explain what's going on here. I'm not an expert, so it's pretty tricky, but we just wrote this. So let's go check if it's right. The nice thing about this book is that it has the answers, so I can actually go look at the answers. So we're in chapter 11, 11, 13, 11.3-I. That's the problem we're working on. Oh, you poor soul. So, he's using a split at function, which I was actually considering doing. And then combining the things back together, but I don't think we need to do that. We can just drop the value. So I think this is probably more convenient to use. Oh gosh. Oh gosh, what did I do? So he's actually using this split at function, but I think this is a lot easier. So we'll do that instead. Lost my spot. Oh, here's my spot. Okay, neat. So that's basically what's going on. So now we're going to write upsert, which is, if you've never done databases before, an upsert is an update or insert for open products. So we need to write a type family to compute a maybe nat corresponding to the index of the key in the list of the type if it exists. Use class instances to lower this kind to the term level, and then pattern match on it to implement upsert. Wild. Okay. So it's like find lm. Don't we already have find lm. But it needs to return nothing. So I think we need this. Whoa, not that. We don't want the stuck type. Basically, we just don't want we don't want this. We just want to evaluate this. Okay. Use class instances. Use class instances to lower this kind to the term level and then pattern match on it. So I think that's something like this function. Hmm. Stomach kind of hurts right now. I need to take like a 10-minute break. But that's gonna put me at like the end of the stream. So, and I need to get off on time today. So I think I need to end the stream now, unfortunately. So when we come back, we're gonna have to figure out what the heck this means. But the goal is we're trying to write essentially the following function. Something like this.